Well, of course, it's always a pleasure to come back to Natal for board meetings, but the special extra of being invited by Dmitry to talk here makes it even more worthwhile. So uh, I wanted to tell you work I've been doing uh, i- in the pandemics. By the way, is this working over here? Okay, and okay, right, seems to work. Uh, Thinking back uh, in the 2000s, I've been thinking of other things, but I've gone back to the idea of, well, quantum chaos, or as Michael Berry tried to convince people to use quantum chaology, which would have been more appropriate. So we have chaotic states, and decades have passed, and we still do not know, uh, have a semi-classical grasp of these states. And of course, there is the fact that, in fact, the what you call chaos, there's a very refined uh, mathematical definitions of things which are usually not at all what exists in nature. The, the real chaotic systems are a mixture of different types of motion, and what is called privately chaos is a subclass of these motions, and there's all other things happening. And but we do know something as we go on. And but but most of this, even though there has been a lot of success with, let's say, purely chaotic systems to look at their spectra and so on, uh, I mean, physics is generally about prodding things and looking what happens when you excite them, and how they react. And there's not been much thought about uh, the dynamics of chaotic systems. So uh, the thing is that, if you look at experiments, there's so much. Quantum mechanics has become a really dynamical uh, activity, not just asking what the properties of atoms or something is, but what you do with systems. And if you look at the experiments, they're all almost always very simple initial states, either coherent states or excited states of integrable systems, such as Rydberg atoms. Now, when you excite a Rydberg atom, you do that, you can get something way up there because you've got selection rules. And this allows you to pinpoint what you want. But if you've got a chaotic system, uh, there's no selection rules. And there's an E missing here. Uh, so, I mean, if you want to excite a particular state up in a very, let's say, consider, I'm going to talk only here of systems which have a classical uh, correspondence. So, all the degrees of freedom are, you can pinpoint. There's no question of a Bose or Fermi system where you do not have something. So, but for instance, if you think of an arbitrarily large molecule or a atoms on a lattice, you can usually pinpoint what they are, and you have a classical and a quantum Hamiltonian. And I'm presuming that at a very high state, this will be very chaotic in a general sense. And if you want to start with something like that, it's not going to be easy. So not only do we not completely understand these states, but they are hard to get at. But on the other hand, uh, going back to work of Bogomoni and Michael Berry, the idea one has uh, used ideas which give you something about individual states, but they are very clear and definite about bunches of states which are have a very well defined energy if you think classically. But this well defined energy, since you're up in a very excited region, may have many uh, actual individual states. Now, there are quantum properties of these states, which are uh, practically universal and to do with the periodic orbits. You've got the shell, the classical shell, and given a few periodic orbits, you can tell what the oscillations of the spectrum will be and what the shape of different representations, like the Wigner representation of this, will be. And you know all this. And so if you want to do uh, experiments one day, if people get interested in this, then probably this is something to get on with. So this is the kind of transitions. So what I'm going to talk about here is, well, we know a lot about what this is just there, but if you prod it, what are the energy transitions that you can look at, right? So let's start defining what we want to. So we get Wigner functions for these states. So these are representations of individual states in phase space, and we put them together with uh, atom in a narrow energy window. So epsilon is the energy window, and E is the average value of this bunch of states. And then so this Wigner function over here, the spectral Wigner function, it represents the spectral density operator, which is this addition of the states. Now, let's get a unitary operator. Now, this is the point I think that needs to be done. That, of course, if you're going to excite things, finding out what this unitary operator is might be the big problem. And if it's not adiabatic and if it's not perturbative, you might have all kinds of difficulties in knowing what it is. But I'm going to start from the point of view that it exists. And if you know what it is, what does it do? Huh? So it evolves the individual states I'm given you, and it evolves then the spectral Wigner function, because you just have the individual states which have evolved, and so you evolve the Wigner function. And then if you ask what the transition probability, the probability density for transition, then it's just a trace of the initial spectral density operator and the final density operator, which in the Wigner-Weyl representation will be just the integral of both the initial and the final Wigner function. No, so that's what we want to calculate. And the fact is that we then have the several approximations for the individual spectral density operators. So as Michael Berry showed, the simplest approximation, drastic, is just to have this the energy shell of the a direct delta function on the energy shell of the, this is the classical Hamiltonian that you have. And so this classical background that we can have is just the integral of the two uh, delta functions. Now, if you look at the Jacobian of this from positions to energy, you find that the two energies, the Jacobian is just the Poisson bracket, and so the classical smooth uh, transition density is just the integral of the Poisson bracket of the two Hamiltonians over their intersection. So here's the picture that I want to see. Now, this is a general picture for any number of degrees of freedom. So you can have a protein molecule, if you want, with huge number of degrees of freedom. But you have an energy shell, which is, you have the 2n dimensional phase space. So it is the the energy shell will be 2n minus 1 dimensional. It's codimension 1. And the other energy shell is codimension 1 also. So you've got a codimension 2, 2n minus 2 dimensional sphere if this is, if both are locally convex, which I uh, say. So your intersection of two spheres will give a dimensional sphere also, and you integrate the classical Poisson bracket over this, and this gives you the classical estimate of what the transition probability is. Now, you see, this is the classical in the sense that if you've got two probabilities and you want to know the combined probability, this is just the integral over both. And the Wigner function does the same thing. That's the advantage of using this lovely representation in phase space. Now, of course, there are corrections, and the true semi-classical approximation of the spectral Wigner function will be will have fringes. It is an airy function. It will be it will decay away from the energy shell, and we'll have oscillations inside the energy shell. And this width depends on Planck's constant. It depends on the curvature of the thing, and this will color the fact that, you see, obviously then classically, if you've got these two energy shells, if you've done such a big transition that they don't intersect, then classically you've got zero. But if you do and when you do intersect, then you get a caustic. It's a huge increase, and then it goes inside. Whereas what the picture that we have here is that, of course, when they are outside, you have, it grows gradually and then it oscillates inside. Right now, let's look at these oscillations now that you get as you come close. Now, what I'm going to jump now into the classical mechanics of this and look at the fact that, you see, where we had two energy shells and they intersect, you can think of this as a Poincare section that one shell takes of the other shell. Now, reminding you, when Poincare looked at systems, he wanted to think of discrete maps instead of continuous motion, and you usually think you've got a shell and you cut it with a plane, right? Now, both of these are codimension one in the phase space, and but two shells are also, their intersection also is codimension one, giving you a codimension two uh, surface, which we have seen. And now you can have the look at the trajectories which go in the shell and cross the section. So if you fix on one of the shells, you've got the uh, trajectory, then it goes around. And usually in Poincare sections, you go twice before you come back. But you can look at what happens after you've gone just one and look at the shell. And this is the kind of mapping that I am going to do. Now, if you've got two shells, you can look at compound orbits, because one shell does a section of your shell, and now you can look, when you've arrived there, you think, no, now I go on the other shell, and when I come back on the other shell. And so if you've got a map for going one way, you've got, if you iterate the map with the second one, you get a compound orbit, right? Now, if you got an orbit and you've got a map now, which is the double map. You've gone one way and you come back the other way, and you just say, well, this is a canonical map. Now, if you look at the fixed points of this canonical map, it represents a trajectory which has come back on itself after these two iterations. So the fixed points of this combination of two maps is a closed, piecewise smooth orbit, which I call then a compound orbit, right? So, I mean, looking at this picture again, before I said that, well, these are the energy shells, but I can say that this picture now can be reinterpreted as saying, look at a single orbit inside of this shell and a single orbit inside of this shell, and it's the same picture, because I can only do pictures in 2 dimensions, and I've got a one-dimensional. Now instead of this being 2n minus 1 dimensional, it's 1 dimensional, and so it is this. And this is the closed compound orbit. And it's got a symplectic area over here, which is its action, its energy action, which is a picture here. And now let's look at the following fact. So you've got a fixed point. This compound orbit is a fixed point of a compound map, a compound canonical map, and it's got parameters E and E prime. Now, it is a fact of classical mechanics that if you've got a fixed point of a map and you've got a parameter and you change it continuously, you get a continuous set of fixed points. So unless there is a bifurcation and then things go, you've got a complication. If you're not at a bifurcation, then you can follow for any E and E prime, you can follow through these fixed points. And so the compound orbits come in families of 2 parameters, E and E prime, right? Now, if they come in parameters of E and E prime, you can also look at the time it takes each part of this. So you've got T and T prime, which are the times, and you can go from the energy description to the time description and vice versa. And so as you change in times, you will get continuous parameters of these compound orbits. Now let's apply this to the problem that we have. So what I'm going to say is that go back uh, to the, now you see, let's distinguish. U is the, what I'm going to, is the driving canonical transformation. Sorry, the driving unitary quantum transformation. And now let's define V as the intrinsic transformation unitary operator that you get just by taking exponential of the initial Hamiltonian, right? This is V of t. Now, the point is that if we know the intrinsic Hamiltonian, the unitary, intrinsic unitary operators here, we can also get driven unitary operators just by noting that if you've got this operator here and you drive it with these unitary operators, it is identical to driving just the Hamiltonian operator itself, because when you do the series expansion over here with lots of u's, they cancel out, and you just drive the Hamiltonian operator itself. So you can just get the new operator here by doing this expansion on the Hamiltonian itself and then taking the exponential. Now, let's then define the compound evolution operator by combining the original intrinsic evolution operator with the driven intrinsic. So this drives the for the driven Hamiltonian. This is the operator that we have here. Now, then let's come in with some semi-classical law, which is that the trace of these unitary operators is well known semi-classically, and it's derived, can be derived within the Wigner-Weyl representation or other equivalent position representations, for instance, of propagators. And it has the following semi-classical form, which is the trace of this operator is very much like the trace of the usual propagator, which gives a periodic orbit. But now this will be a compound trajectory, and there will be the action, which will be the time action. That's not quite what I said before. And there is a prefactor over here to do with the local motion around the trajectory. Now let's define what this is. The action of this, the trace of this trajectory. So let's relate this, which is coming in here, right? If you add et and e prime t prime, it will be that symplectic area of the compound orbit, which I showed before. And it can be shown generalizing what one knows if you just have one energy and one time, that the partial derivatives of this will be given by time and energy, right? Now, with the stability matrix. You see, this is the stability matrix about the orbit, but now if you've got the stability around the orbit going to one intersection, and then you just take the product of that with the next one, you get the full stability around the that. So you just take the product of the two stability matrices. Uh, Now, one when one does with a periodic orbit, there's the fact that when you come back, there's a direction which is not which is trivial because it's on the orbit itself, and this is not true here. So there's generally a reduction of dimension when one uses it for a periodic orbit. So this is a technical detail over here that uh, I'm using full stability matrices over here. And of course, if you've got if let's say you've got near tangencies and one of the the energy shells is nearly the part of it which is touching the other is very small, then of course you get a periodic orbit as a limit. So, but of course, another difference is that if you're looking at a shell and look at the periodic orbit, there's a minimum periodic orbit period. But if you get two which are intersecting, you can have arbitrarily small periods coming in, so there's no restriction like a periodic orbit. Now, here, this is my most complicated slide, but it's not so bad if one look at it. Now, what I'm going to say is that the spectral, I have been concentrating on, now this is the Wigner-Weil representation of the intrinsic unitary operator. So it's the Wigner-Weil propagator for the initial energy. And you take the Fourier transform of this with an energy window, will so it's a cutoff in time, gives you exactly the spectral Wigner function from which you started, right? Now, then to look at the exact transition formula, I get two copies of this and put it in, right? Now, this is then this over here, the spectral Wigner function for the initial state with energy E. And this is the spectral Wigner function for E prime in the driven system. Now, switching integrations gives me then a double Fourier transform of this integral over here. And this integral over here is just the trace of the compound propagator, but compound of the propagator of the intrinsic propagator for unitary operator for the initial Hamiltonian and for the driven Hamiltonian. So you've got a double, my final formula that then is here, an integral for the transition density is a double Fourier transform of the trace of the compound propagator, which is what we know semi-classically already, right? Now, there will be many terms coming from, you see you've got positive and negative In this integral here, you've got positive and negative times. So you can have any integral which for plus for t equals positive or negative, which for which this has a stationary phase solution will come in all possibilities here. Uh, but they will come in pairs, and then they will give complex conjugate elements which make this real over here. Now, so coming quickly to conclusions, when you do the stationary phase approximation to this these double time oscillatory integrals, what you then get is this. Here is the these are going to give oscillatory terms which are to be added to that smooth classical background with which I started. Now, this over here then is the action of a closed compound orbit, right? And this, it's got, so you've got cosine oscillation of this. So as you change E and E prime, you this oscillates. Also, of course, the driving time that you might have put in is another parameter. So it's a driving parameter here, and the energies that you put in. With any of these, you will get oscillations. Then there is the energy window, which cuts off very long orbits, depending on your choice of energy window. You've got a determinant over here, the Jacobian of the same. No, it's the Jacobian between time and energy over here, and the term now, which is the this gives you the stability of the compound orbit. So it's the product of the two stabilities for each segment over here. And so the J prime sum includes all trajectory segments in the E shell and the driven E prime shell, right? Traveling forward and backward in time because of we had the integration from plus or minus infinity before, which all of the ones which combine to form closed compound orbits. So the long segments are exponentially damped with this energy with epsilon, and the non-oscillatory contribution, you can consider. You see that I've had Poincaré maps for given times, but there's the in the integral there was the contribution from very small times as well, and that contribution is just a classical background which I described to start with. Right? So what one is finding is that for energy transitions, you have a similar situation to what one has for the static case. In the static case, you look at the trace of the evolution operator, you take its Fourier transform in time, and you get a smooth density of states, right? Now, if you make a semi-classical evaluation of this Fourier transform, you get periodic orbits in the energy shell with repetitions, right? And this is the, let's say, it's tantamount to the Gutzwiller trace formula, even though I think that Gutzwiller himself was not thinking of energy windows. I think that Bogomoni and Berry are the ones who put the, let's say, they created a context in which the Gutzwiller transform is actual good approximations immediately without any thing. Whereas Gutzwiller was hoping to that this would give individual states. So the defocusing from individual to energy windows came later. Of course, then there was an effort to do resummations to arrive again at the squeezed individual states. But I think that this huge effort to get the individual states defocus from the fact that we do have good quantum knowledge of something which is worth knowing about chaotic systems in quantum mechanics. Right? Now, when we want to look at the trace, if we start with the trace of the compound evolution operator, you take its Fourier transform in double time, and you get a smooth density of energy transitions. Now, if you want to do this semi-classically, you find that the oscillations of this transitions are given by the closed compound orbits that join the energy shell with the driven energy shell for the other energy that you want. And so you've got a compound trace formula. So, final discussions. The first is that universal imprint of energy transition density oscillations. So universal here is that nothing has come in here about the, you see, one is using finite times. So it does not matter whether the actual in Hamiltonian, of which the eigenvalues we're talking of, whether this is integrable, whether it is purely chaotic or mixed chaotic, you have individual trajectories which come in whatever the dimension of the system. The description is the same of what one is obtaining, right? So in this sense, it's a universal imprint of the produced by arbitrary unitary evolution, which I have not specified. I have hidden in here all the Wigner-Weil, the instruments that I have used to get the result. But the point is that one finds that the results do not depend on the representation which was used to obtain them, right? And one finds that the amplitude and the phase is not at all constrained by the. So I use that to do the phase stationary phase integrals, but I have not the result does not come out. Now, of course, one doesn't usually have the full knowledge of this unitary operator. So, what in practice, I think that this can be used immediately if you've got a kick, a sudden jump, and this gives you the final what the whole effect has been, and otherwise you have to solve the Schrödinger equation to get this. Even though, of course, in using the Wigner-Weil representation, you are not constrained to the Schrödinger equation in the sense that you're not constrained to a second order partial differential equation. Your Hamiltonian can be completely arbitrary and you can get the results even so. Now, even if you think, well, so you do not know, I said your unitary operator, which is the exponential of the Hamiltonian, the driven one, is given by driving just the Hamiltonian. But of course, you do not have this quantum mechanically, and even classically, in classical mechanics, if you're not, I think no amount of numerical work. You see, classically, you can get your Hamiltonian, you do a canonical transformation, you get the orbits, and you know where they go. Now, you get a finite number of orbits. But if you're going to look at what happens, consider the driven Hamiltonian as something that you get your hands on, you have to do Hamilton's equations with it. And then you have to take derivatives to get the trajectories. And you cannot depend on these trajectories if you have done this all numerically, which is, so you have this numerically. So for instance, getting the classical approximation of the overlap of the two things, you can do lots of orbits and integrals are all right if you do numerically. You do Monte Carlo and you get all these trajectories and you find out what's come out and you do good integrals. But if you want to differentiate to get the driven trajectory, that's difficult. So what I want to conclude is that since in this year now, I have got a generalization of this for arbitrary time-dependent Hamiltonians. So, for instance, you can have your what I called the driving Hamiltonian can be a perturbation, a time perturbation of the initial Hamiltonian, and it can be an arbitrarily large perturbation. There's no problem. Now, what does one do then? This is new. The work is not out yet, but I can give you the idea. So what I was doing before, you see, you had your two pairs of your pair of energy shells, and you drove the energy this shell, and it became the driven shell, and it intersected this initial shell at the other energy. Now, this is what the closed compound orbit was here and here. So here are the shells. Inside the shells, there are the compound trajectory, which is the fixed point of the Poincare maps. Now, what you can do is it's a complication, but just as you got this section over here, you can get this shell and propagate it backwards in time, and you get another Poincare section here. Now, you can then join what you can now do is that you look at the compound orbit, which instead of being this one with this one, it is it is on the initial E shell, you come down to the other shell, and then back on the initial shell over here at E prime and come back. So you've got a fourfold compound orbit, which are the continuous curves over here to make your compound orbit. And there is a consequence of the Poincare-Cartan theorem tells you that the action on this orbit that we do not know is actually given by a combination of going here, coming here, and coming here, that the the action on this quadrangle over here is zero, so you can switch from this orbit here to going all the way here and coming back. So that even though you will have compound orbits now, which are fourfold segments, you've got 4 segments, 2 red and 2 dark black. You each segment is given by a single pre-established Hamiltonian. You're not thinking about the trajectory of a Hamiltonian which you do not really know how to construct. Here you've got then 4 segments of the 2 Hamiltonians that you do have. The initial Hamiltonian, which is the black, and the driving Hamiltonian, which is the red. And so I think that's so this is coming out now. It's nearly over. So, but then I think that we can do. So this is completely non-perturbative energy transitions for arbitrary evolutions. So that's what I wanted to tell. Thank you.